now I want to return to integrals using those ideas of limits. We have here what's called an improper integral. As an example there, we're integrating from 1 to infinity of 1 over x squared dx. What makes this improper is this really has no meaning, right, as far as how we defined what the definite integral is. Our definition is from some constant to some other constant, and infinity is not a number. So we need to define what we mean by this. So what intuitively we mean is that what happens as you keep integrating farther and farther and farther and farther out. So that's precisely how we'll handle this. So what we mean, and if we want to think about this graphically, what we really mean is what happens if you integrate, say, to some location, some finite amount, right? That's a proper integral. It's going from some number 1 to some number b. And then what we really want to know is, do you approach anything as you keep adjusting that upper limit and making it larger and larger and larger and larger? So what we really want to mean by that integral is the limit as b goes to infinity of the integral from 1 up to b. So now this is what we're going to define that to mean. When we have an integral to infinity, what we really mean is have that upper limit be finite, but then see what it approaches as we let it go to infinity. And so you can think of the limit now is outside of the integration. So we just proceed as we normally would with our integral, and then we'll just apply the limit after the fact. So this is the limit as b goes to infinity. The antiderivative there would be negative 1 over x by power rule. So negative 1 over b minus a minus, so plus 1 over 1. And actually, if we just stop here for a second before we do the limit, what we found is that at this stage, that area we have there is negative 1 over b plus 1. And then as we grab that upper limit and slide it out farther and farther and farther, this little term in there is heading to 0, and we're approaching 1. So that's what we mean, is that we say that that integral equals 1. And what we mean by that really is that it approaches 1 in the limit. That as you go farther and farther out with that upper limit, the accumulation you're getting from that integral is getting closer and closer to 1. And this is not a purely theoretical thing, you might think, because it involves infinity. This is actually a classic example from physics of calculating escape velocity. It revolves around this equation. In calculating escape velocity in physics, you look at, we looked at work already, right? And that when you raise stuff up to a higher height, it has more potential energy. Well, if you're trying to launch something off of a planet or moon, we look at, well, how much kinetic energy would you have to have at launch so that you could use all that kinetic energy to escape gravity, which would essentially mean going infinitely far away. And so you do that work integral to infinity and figure out how much energy is required, and that you can use the kinetic energy formula to figure out the escape velocity. So there are other examples too. So this is not purely a theoretical thing. Really, integrating to infinity is something we want to do in practical application. So the thing we have to understand, though, is we need to have a definition, because what we've defined so far in calculus does not cover this. So our definition is going to be what we mean by the integral from a to infinity of any function is that we're taking the limit as b goes to infinity the integral from a to b of that function. Likewise, the lower limit could be negative infinity. And so we could go from, say we were, so here's one of our definitions. Here's another one. What do we do in this case? Well, same thing, right? What do we want to mean by this? We want to mean let that lower limit slide farther and farther to the left and see what happens. So we want to take the limit as a approaches negative infinity of the integral from a to b of f of x. And then lastly, we could integrate across the entire real line. In statistics, we're often interested in integrating over what we call a probability density function. We want that integral from negative infinity to positive infinity to be 100% chance of being anywhere, right? So if you take some probability in statistics, you'll often see this integral integrating some function from negative infinity to infinity. So we have to understand what we mean by that. Well, all we can do is just use our properties of integrals. We're going to say that let's break this up. So we're going to define this to mean the integral from negative infinity to some value c of our function plus the integral from c to infinity of that function. And now those two integrals are those already defined. So this is defined as the two of the previous put together. And we'll look at examples. So we've seen an example of 1. We'll look at examples of 2 and 3 as well.